Дорогие коллеги, друзья, добрый день. Мы начинаем наше заседание.
Dear colleagues and guests,
доктора геолого-минералогических наук Gurzhiy.
we'd like to start the meeting of the Dissertation Council for the defense of the thesis by Gurzhiy Vladislav Vladimirovich for the degree of Doctor of Geological and Mineralogical Sciences in the scientific major 164, Mineralogy, Crystallography, Geochemistry, Geochemical methods of respective minerals. On the topic, the crystal chemistry of natural and synthetic uranyl sulfates, selenites and selenates. I'm happy to see so many of you present today in this hall. There is a special order and the procedure. By order of the Academic Secretaries in Universitetskaya University, Knotov Alexander Valentinovich, dated 10th February 2022, number 1001/1, Brusnitsyn Alexey Ilyich, Doctor of Geological and Mineralogical Sciences, Professor of the Department of Mineralogy of St. Petersburg State University, was appointed Chairperson of the Dissertation Council. The same order appointed the members of the Dissertation Council. Pilatov Stanislav Konstantinovich, Doctor of Geology and Mineralogy, Professor of the Department of Crystallography, St. Petersburg State University. Burukov Boris Evgenievich, Doctor of Geological and Mineralogical Sciences, Senior Researcher, Russian Academy of Science. Pushkin Denis Valeryevich, Doctor of Chemistry, Associate Professor, Executive Director of the Faculty of Chemistry, Head of the Department of Inorganic Chemistry, Samara National Research University. The following members are present in the remote access mode. Sokolova Yelena Vladimirovna, Doctor of Geology, University of Manitoba, Canada. Yelena Vladimirovna, can you see and hear us? And Stickenberg Alexander Grigorovich, Doctor of Geology and Mineralogy, Professor, Department of Chemistry, Faculty of Arts and Sciences, New York University, United States of America. Can you see and hear us?
Замечательно, мы вас тоже все слышим.
Perfect, we can see and hear you as well. The applicant, Gurzhiy Vladislav Vladimirovich, is also present at the defense, as well as the scientific advisor of the applicant, Doctor of Geological and Mineralogical Sciences, corresponding member of the Russian Academy of Sciences, Professor of the Department of Crystallography, St. State University, Sergei Vladimirovich Krivovichev. Audio video recording and broadcast being carried out, and simultaneous interpretation is being carried out from Russian into English and vice versa. On the screen of live broadcast, one can see the email address to which it is possible to send the questions related to the content of the thesis. Technical services will send me those questions and I will voice them. The questions should be directly related to the applicant's thesis. It is necessary to indicate the name, position and place of work of the author of the question. Otherwise, questions are not to be voiced. Questions not related to the thesis and anonymous questions will not be voiced as well. In accordance with the procedure for awarding the degree of Candidate of Science, the degree of Doctor of Science in Petersburg State University, approved by the local regulations of Petersburg State University, a meeting of the Dissertation Council is considered competent if at least 2/3 of the approved members take part in its work, but no fewer than 4 people. Our Dissertation Council consists of 6 people, all 6 are present, including 2 council members in remote access mode. Thus, there is a quorum. Like the member of the Department for Ensuring the Activities of the Dissertation Council, the Curator of the Defense to issue the turnout sheet. The procedure of today's meeting is as following. It consists of 16 points. First, brief information about the chairperson, about the applicant and the documents submitted by the applicant. A short report by the applicant on the main provisions of the defense. We have discussed this question, and the report is going to last 40 minutes. Then questions and answers, then reviews by all the members of Decision Council, speech by the member of Decision Council, and the answers of the applicant to the remarks and questions. Next, an open discussion when all those present in the hall might be able to voice their opinions. We would like to ask all those willing to take the floor to sign your name in the turn-out sheet, indicating your job title and position. Voicing the questions received via email during the live broadcast. Speech by the scientific advisor. Discussion by the members of the Decision Council, then open roll call, making decision whether or not to award the degree, and then the closing remarks of the applicant. Finally, the time of the defense is about 3 hours, the time limit. Are there any questions concerning this procedure? Since there are no questions or objections, we may proceed. All those present in the hall are asked to switch off the sound of your mobile phones, but the colleagues in the remote access mode are asked to turn on your mobile phones in case of technical failure. So, a brief report about the applicant. The thesis by Gurzhiy Vladislav Vladimirovich for the degree of Doctor of Geological Mineralogical Sciences, Scientific Major 164, Mineralogy, Crystallography, Geochemistry, Geochemical Methods of Prospecting for Minerals on the topic, Crystal Chemistry of Natural and Synthetic Uranil, Sulfates, Selenites, and Selenates. Was accepted for defense on the 20th of January 2022. Gurzhiy Vladislav Vladimirovich completed the thesis and submitted it at State University. His scientific consultant is Doctor of Geology and Mineralogy, corresponding member of the Russian Academy of Sciences, Sergei Vladimirovich. The number of applications by the applicant, which outline the main provisions of the defense, according to the list, 39. In peer-reviewed scientific publications from lists approved by the Ministry of Education and Science of the Russian Federation, 2 publications. In publication in the Scientific Databases Web of Science and Scopus, 37 publications. According to the information I received from the curator of the defense, all the documents submitted by the applicant meet the requirements established by the University universities and are stored in the applicant certification file. The copies are in the possession of the Department of Supported Activities of the Decision Council. Dear members of the Decision Council, do you have any questions to the applicant? Is it necessary to voice the entire list of the documents submitted for the defense? There are no questions, and there is no need to present the list. Then I'd like to give the floor to Vladislav Vladimirovich. The floor is yours. Dear members of Decision Council, dear Chairperson, thank you very much for this opportunity to speak in front of you today, which is dedicated to crystal chemistry and uranyl, sulfates, selenites, and selenates. The history of studying uranium allowed scientists some interesting data. Martin Klaproth, which were who worked on these compounds proposed to call the new compound Uranus, based on the planet Uranus. But it turned out that he found the oxide form and not the metallic compound. And only 50 years later, it was possible to find this element in its clear form. There were many stages in the history of studying uranium, but I'd like to focus on the words by Mendeleev, who, starting from the fourth volume of his Basis of Chemistry, said the following: "Convinced that the study of uranium, starting from its natural sources, will lead to many new discoveries. I boldly recommend that those who are looking for subjects for new research should pay special attention to uranium compounds." And we can say that we followed this piece of advice when we were doing our research. So what do we know about its natural forms? There are about 300 uranium minerals in nature. About 250 contain U6+ uranium. The remaining 50 mineral types contain uranium 4+, like uraninite, which is natural compound, very important for our nuclear industry. Or some minerals where uranium is an impurity. The formula of one of these compounds you can see in the slide. And we can see that the uranium ion 6+ is in the structure of this compound. Secondary minerals are uranium, and we'll be talking about them in particular and their synthetic analogues. You can see a number of groups on the slide, and if we conduct certain statistical relation in the structure databases, there are about 1,500 structures, compounds in inorganic, crystal compounds which contain hexavalent uranium and 4-valent uranium. Crystallic structure contain more than 5,000 of such complexes. It is rather complex chemistry of compounds. If we don't focus on metal-organic compounds, and among these more than 5,000 samples has the majority of such, we can see that chain structures are less popular. There are some layer structures. There are several nano-sized complexes as well. If we talk about the complex of these natural compounds, then sulfates and phosphates are on their first position, and selenites, which will be discussed today, are about 7. And since we'll be talking about natural chemistry and synthesized compounds, we need to say that synthetic compounds of uranium 6+ are selenates, more than 150, and sulfates, about 130 structures can be identified. But these are inorganic compounds, or inorganic uranium-containing compounds, which has proton organic molecules. It's worth noting that selenium is a very interesting element if we talk about radiochemistry, fission chemistry. it has about 53 grams per ton after 3 years of fuel irradiation in the reactor. So this can be found in the nuclear waste. As a result of the acidation of primary sulfates, such as berthollinite and tractylite, acid solutions are formed, which can be considered the analog of acid drainage, technogenic acid drainage, which influences uranium-containing rocks, moving it into mobile form by oxidizing uranium to uranium-6+. Uranyl sulfates and uranyl selenites are formed. It's necessary to focus on the way the minerals look because they attract the eye. These are yellowish and greenish types of minerals which you can't pass by. If we talk about the compounds formed as a result of technogenic influence, then uranium 6+ were found on the surface of lava as a result of Chernobyl accident, and colloids of uranium were found 3 kilometers from the source of contamination, Lake Gurzhiy, not far from the city of Azovsk. Which means that studying the structure, which is the key source of information, the direct source of information about the element, and this knowledge is important for the modern civilization to understand the migration capabilities of an element, the ability to form insoluble phases, so as to know how to influence the environmental safety. Characteristic feature of U6+ ions is the formation of linear complexes, which is called uranyl ions. The oxygen atoms of uranyl ions are completely valence saturated, and the valency of the bond with equatorial atoms is rather low. For the atom of oxygen is about 0.5 of the unit. Thus, horizontal polymerization is formed. Thus, layers and chains in a way are formed. On the slide you can see the traditional, the classical form of polymeries. These are pentatetra or hexagonal dipyramids or trigonal pyramidal complexes with the atom of selen in the apical position. This is how it looks. In the report I talk about different ways to describe these units. For rare structures where polarization is formed through joint vertices, we use graphic approach, and we use gray for the epoch. If polymeries of uranyl or other cations are linked through the edge, then we make two lines to show the links. If it is jointly joined by the edges, then we use the topology methods where we have only equatorial anions. And thus we get a range of hexagon following group is the most widespread. It is rather representative. About 50 mineral species can be found. In here you can see 15 minerals, which are different cations. And the uranyl sulfate layer can be seen in the slide. This layer is linked to the solid structures. These are solid chains from pentagonal pyramids of uranyl, which are edge-shared with sulfate complexes. Apart from such structures, we know such minerals as uranophyllite, which is formed according to the simple strategy. We can see the chains, hexamers from pentagonal pyramids, which are linked through tetraeds, and minerals, geochemite and deleensite. The topology of them is that they are solid structures. That's phosphor-nailite topology, which crystallize from the compounds. The examples that I've given are the examples that are well known, starting from the first discovery of uranyl compounds. Currently, in the mines, compounds are emerging, the structure of which is based on the rare complexes, environment complexes, where via tetraedric oxonions we see the compound of through the common edge, and you can see the structure of these minerals on the slide. The following slide provides you the general systematic classification of uranyl sulfate compounds and minerals. And the majority is formed by the complexes containing solid structure of correlation polyhedral. During laboratorium tests, we decided to study what thermodynamic parameters influence the crystallization of the compounds, and we conducted an experiment. We took the synthetic analog of scoopite, and we put it in a hydrothermal environment for 24 hours, temperature 110 degrees Celsius, with subsequent evaporation at room temperature, and 4 new phases were obtained. 2 of the phases were obtained directly after the experiment. Once it was opened, at the end of the capsule, the crystals of these 2 compounds were present. And both of these compounds are linked to solid structures and can be viewed as part of topologies. One was studied by our colleagues from Samara, which is the analog of natural compounds with CBI structure. As a result of evaporation at room temperature, we obtained 2 remaining phases. They were obtained without heating, but from previously heated solutions. And we don't see edge sharing of polyhedras of uranium, but we can see that of sulfate oxonions. Having studied research, we found that there was a certain evolution of these structural units from insolents, which can be found in the following minerals, to more complex structures. We can see chain link, and then finally the layer link or sheet link. As a result of the experiments, studying the experiments on the influence of temperature on uranil, we used hydrothermal method, but at twice as low temperatures. The temperature was slightly above the room temperature, which can be obtained at certain deposits in Africa, in Congo, for example. As a result of the experiments, we contained 8 uranium-containing phases, 6 of which were new ones. And you can see their structures in the slide. One of the new compounds is a carcass structure, which is not traditional for uranyl sulfate chemistry. But it's interesting to note that apart from getting new phases, crystallization begins with such a phase that's the calcium sulfate of uranil, synthetic analog of the mineral Gurzhiy. So the system is rather active and vivid, and this mineral similar phase, this phase was sustainable from the beginning till the end of the synthesis, which means that complex processes might take place non-observed by the scientists in natural environment. And we can identify several natural phases, some of which are metastable, and they do not crystallize till they get microscopic view. If we talk about selenites, we are not talking about the sulfates right now. We'll be talking now about selenites and selenates. We conducted a detailed crystal chemistry analysis of the complex. 24 out of 39 synthetic uranyl selenites were obtained by hydrothermal synthesis. 2 compounds remain without clear structures, but according to the equilibrium of perimeters and of symmetry, we can put the remaining 2 minerals into the group of 5, which crystallize in such structural form. This structure is based on layer uranyl-based complexes, has solid architecture. We can see edge sharing, two remaining minerals are highly interesting. Their structure is based on chain structures, but not on trivial ones. On the one hand, the topology of the chain complex in adagrexic mineral is rather common. Chain topology for uranil compounds. But organelle dipyramids are polyedrous in here, which is rather rare in synthetic chemistry, and it's impossible to get such complexes if we synthesize compound at room temperature. This mineral contains more complex chain structures which are not that common. But But if we talk about the structural chemistry of uranium, there are several representatives of such structure. But the existence of this additional apexes, of the white one, we can see the additional selenite group, and we never obtained those with evaporation at room temperatures. If we consider all the known materials, all the known research based on selenites of Uranil are obtained by hydrothermal methods with the temperatures from 102 to 120 degrees Celsius. And 4 compounds were obtained at temperatures above 350 degrees. And only 11 compounds, mainly rarefied, were obtained at room temperatures. And chemical analysis of natural and synthetic selenites and uranyl sulfates indicate that the formation of structures with dense topologies, solid topologies of the end junction of the coordination polyhedra is associated with elevated temperatures. And the vertex type of polymerization of the coordination polyhedra is observed at room temperature. But the complexity of crystal structure can be quantified by the amount of Shannon information it contains in bits of binary digits per atom, which means bits per atom or per cell. That's kind of a parameter that we can use to mathematically calculate the complexity of a specific crystal structure. And it's interesting to note how the parameter of complexity correlates with the structural types. But if we took into account not a single parameter, we calculated these characteristics for different domains. For example, for uranium-containing structural unit, separately for the molecules of water, separately for interlayer cations, which compensate the uranyl-containing complexes. And it was interesting to view the symmetry and the complexity of the topology. During the research, we noted that very often the symmetry of this interlayer or interchain block is lower than maximum possible. That is topological symmetry. The main influence into the complexity is made by interlayer complex and the system of H bonds. If we look back to the previous picture about the evolution of structural complexes, with such combinations of polyhedral, natural and synthetic compounds, we can evaluate how important different blocks of structural complexity, topological complexity, and interlayer cations are important. And the result is very often determined by the topological complexity of uranyl sulfate complexes. So what we get is often crystallized with the maximum possible symmetry for the structure itself and for uranyl containing blocks. I also mentioned the similarities of natural and synthetic uranyls uranyl compounds. The structures are different, and not only in the chemical way, but in the organization of the structure as such. All the known natural compounds, which belong to layer groups which have definite structures, are formed in this way. The layers are the same as in synthetic compounds. It is a little bit more condensed in a way, and additional cations and water molecules find it much difficult to get. But we can see these layer complexes to the right based on the principle of the stairs in a way. And the parameters of the complexity of the structures are lower than in the minerals, which have their complexes based on similar, genetically similar topologies. And in here we can see the topology of one of the elements. This slide provides statistical information based on the parameters of the difficulty of the structures of selenites of Uranil. The majority of synthetic compounds have topological symmetry, and the highest symmetry remains despite the interlayer structure, which shows how the cations and water molecules influence the compounds. Here we can see the contribution of topological complexity to the total information complexity. And we can see how these parameters are distributed. And the second provision for defense, the contribution to the overall complexity of mineral structures is made the contribution of topological complexity to the total information complexity for most natural uranyl sulfates and selenites is no more than 30%, while the main contribution is made by interlayer or interchain cationic complex and the packing of H2O molecules. We were able to synthesize calcium uranyl sulfate into such a structure. Before us, sulfate analogues was synthesized by our American colleagues from the University of Notre Dame, and not so long ago, the natural mineral was found in nature, the compound of calcium uranyl sulfate, which made us think about synthesized sulfates of uranil and selenates of uranil. Can we draw a parallel between them based on the structural complexes? Starting from the middle of the 19th century, thanks to the works of Michelik, who demonstrated the isomorphism of selenic acid.
Это калиевая система, смешанная сульфат-селенатная система, да, с уранилом и с...
The first system we focused on was the Kalium system, which showed that everything was not as easy as Michelik thought. And within this structure, we caught 4 crystal structures. And in here you can see the fragments of these structures. They all begin to the layer complexes, but their topology is highly different. In the slide you can see the graphic representation of these structural complexes. They all belong to rarefied structures. We crystallize them at room temperature from simple solutions. And depending on the tetraedric position, we can see the different speed of isomorphism of sulfur and selene. So there are solid complexes, as you can see with the red spot, where selene does not get into despite its presence in the solution. And in tetraedic oxanion, when it feels rather comfortable to change its geometry and size, and selenium thus can enter into such positions easily. So depending on the coordination of this tetraedic oxanion, we can expect a different speed of isomorphic substitution. The next system is Cesium, compound of Uranil. And here we did not find any structural complexes within one system. From sulfate to selenate phase, only one structural type crystallized. And the speed of replacing selenium into sulfur was not the same. You can see here tetroides with 4 edges, and in the second picture we can see tetrades with 3 edges. And if we talk about 3-edge complexes, we can see the linear correlation of selene entering the structure. For 4 sharing tetrades, then the speeds were very low, more than 60% of selenium, and a little bit more than 20 got into its structure. A very interesting point is that crystallization in selenite system starts with such a compound, which is highly rarefied, with different geometry and architecture of layers, which was synthesized by our colleagues from Samara. This crystals crystallized and became soluble. It's interesting about when we talk about stable and metastable compounds. The structural complexity of the structures with 4 sharing tetrades is a little bit higher than the complexity of these metastable crystals. So less stable compounds very often become metastable. When we started the experiment on bivalent cations, we identified 3 different structural types which have the same chain complexes. But because of the shift of tetroids in pseudo layers, the symmetry is different, thus we can say that they belong to different polytypes. The complexity of crystal structure for the middle complex is higher than for the remaining 2. We can see monoclinical crystallization, and this excessive symmetry is more stable. Later on we can see the crystals of this phase in the following synthesis. So we started identifying these crystals in the synthesis where they previously were not seen. Rietveld with ferrum was also discovered, and its structure is in the form that we identified. The other bivalent cations, a pH of the solution from 1 to 1.1 till 4 increases the speed of crystallization up from 2-3 weeks to 1 or 2 days. And we can assume that this mineral was obtained from the solutions with pH from 2 to 4. This is the work of 1996 of our colleagues. Demonstrated a similar principle. The extreme members of solid solutions can be crystallized, and the symmetry is increased if we mix different types of cations. Based on the experimental data, it was shown that selenate 6+ ions mixed uranyl sulfate selenates demonstrate preferential occupation of tetrahedral positions with lower topological connectivity. In a number of cases, incorporation of selenium 6+ leads to the emergence of new structural topologies and changes in the overall structural architecture. Then there are compounds with organic elements, which were previously studied by us. In this slide you can see different geometry compounds.
Амины, диамины, да, различные разветвленности, размеры, формы. Ну и в случае молекул с аминами формирование.
In case of molecules with aminites, the structure formation is obtained by direct contact of organic and inorganic substructural units through hydrogen bonds. Thus, the size and shape of the organic molecule affects the diversity of the structural architecture of uranyl complexes, which we observe. And we introduced the principle of hydrophilic and hydrophobic zones, which means that hydrophobic zones of an organic complex are associated with a space of large hollow rings of inorganic complex, while hydrophilic zones tend to dense aggregates of small rings, which can be seen on the slide. We can see some vacant space, and aminic groups tend to be found in more dense groups. This was one of our works, and it proved our hypothesis and our ideas. And hydrogen links may influence the symmetry of crystallic structures of heavy uranium-containing compounds. We deciphered a number of compounds and decoded a number of compounds. The topological symmetry of this uranyl-containing complex is high. It is sometimes tetrahedral, but the bridge atoms of oxygen are moved from their initial positions, and thus symmetry is lost. If we take complex molecules such as zirconium or others, it leads to crystallization of very rare topologies which have high complexity. Out of 4 obtained compounds, 3 compounds were new, and 1 compound crystallized in a very rare topology, although a known topology. And the complexity of such structures is much higher than we usually obtain as a result of the experiment. And the fourth provision for defense, interplated organic and inorganic selenates and uranyl sulfates, the general architecture of the structures, the topological and geometric characteristics of the organic complex are determined by the configuration of the hydrogen bond system and the balance of hydrophilic-hydrophobic interaction. In here we are going to talk about the evolution caused by dehydration. Within one synthesis we obtained 4 different structural units. Unfortunately, it wasn't possible to identify which of them crystallized first and which one crystallized next, but we can compare their structures from chain simple to chain more complex one to layer structure. It is possible to identify 2 evolutional branches of dehydration. With the loss of water with its substitution to the hexanium complex. The second, with the loss of water and increase of the dimension of the crystal structure. And if we talk about the dimension, there is a very interesting approach. The decrease of the size or dimension with the increase of reduction agents such as water or tetrahedral complexes. And we conducted an experiment for all the known compounds with monovalent cations and put them on these triangle diagram. For example, this is the point for this inorganic compound, or several might be seen in one point since they have a similar formula. Thus, having put all the dots, all the points on this triangle, we found the sheet complexes and separate clusters. And when working on the thesis, we put the new compounds that were developed within the period following this work and that we conducted during the thesis research. A decisive role in increasing the dimensionality of uranyl complexes in the crystal structure of synthetic and natural compounds with a general formula are played by organic and inorganic cations and water molecule, which act as dimensionality reducing agents. Well, as was mentioned, a lot of printed works were published based on the materials of the thesis. The structures of about 170 compounds were clarified. Well, thank you very much for the attention. Thank you, Vladislav Vladimirovich. Dear colleagues, now I would like you to voice your reviews and ask questions addressing the public in the hall. And all the colleagues in the hall, you're welcome to ask questions. What's the mechanism? It's difficult to be more specific. Our research was mostly based on low temperature synthesis. We didn't use high temperature synthesis that often. If we look at the information from literature, many people all the researchers use similar temperatures. For example, 100 degrees or 220, like all the others use. We were trying to change these limits, so we used 50, 55, and it's difficult to provide general assessment. But the boundary of about 70 degrees, that's edge polymerization, not depending of the type. Uranyl sulfates polymerizes at a lower temperature. If we take about 100 degrees, then we can synthesize uranyl complexes. In our work, pH environment influences the quality of the crystals obtained, well, in specific intervals, so to say. If we talk about the temperature, we took the limit when beyond that we didn't get the result in polymerization.
Извините, говорите в микрофон, вас плохо слышно. Микрофон рядом, говорите прямо в микрофон.
Can you hear me well now? Thank you. In your opinion, how can the results that you obtained can be used for different classes of uranyl compounds, such as oxalates, probably, which are similar to sulfates in a way? I think it's not so easy to use this information if we talk about oxalates. Not so long ago, they were mined in the state of Utah by our American states. So oxalate uranil is not only a synthetic compound, but there is a natural compound. But if we talk about sulfuric acid, it's significantly different. And oxalate radicals are edge binding agents, so the chemistry is different. Probably there are some similarities, and minerals in natural environment grow in similar environment, but I suppose that local chemistry is of crucial importance there. Can you hear me? Vladislav Vladimirovich. The first provision for defense, you talked about the general element of polyhedra was substituted by edges. But the second factor is the pressure. And the pressure is very common. If we talk about from the move from the apex to the edge, that's a very interesting aspect. If we talk about average hydrothermal synthesis, then the pressure is present. Since the system is closed, the pressure of the water vapor is present in this closed system. But we conducted a number of experiments in hydrothermal environment at low temperature, pre-boiling temperature, at about 55 degrees in open systems. So we didn't use the experiment until all the water is evaporated, but we obtained the similar results. So pressure does play a role, but at the same time, the pressure plays a role in natural processes taking part in deep in the earth crust. So thus we can talk about the secondary mineralization in the mines. If we go deep, then we can see the importance of pressure. But on the surface, the pressure doesn't play such an important role, and such minerals are still found. Maybe it also depends on transportation. But we diagnosed in the synthesis and synthetic experiments this similar situation. Did you measure the pressure? If so, how? No, I personally didn't measure the pressure. Our systems are rather simple without a manometer. But if we have a look at the previous experiments, there were similar experiments conducted with the calculation of the pressure. In our case, this wasn't very high because the temperatures were rather low. It was a pre-boiling temperature and boiling temperature, and the pressure is not that high.
Спасибо.
Спасибо. Еще вопросы, пожалуйста. Евгений Борисович, у вас есть вопросы? Нет? Коллеги.
Colleagues, any more questions, please? I have a couple of questions. Can we have a look at the slide 15, please, once again? Yes. It wasn't that clear in the report, but in your research paper you said that sometimes you say about uranil as cation. Take your seat and speak in the microphone. And in other cases, you talk about it in the anion complex. So which is the right option? I suppose that there is a flaw in my presentation and in my research paper. We took our initial data from the papers of other authors. Sometimes these were older experiments. It's better to put uranil in brackets, showing its oxyanion part of a sulfate and selenite or selenate complex. I would consider it a more appropriate option. If we combine uranil with other anions into complexes, like in here, a wash group, water groups, and other groups, is it right to call these compounds as you put it in your name of your thesis? Uranil sulfates, uranil selenites, if they are anions. I'd say that's a rather philosophical approach. Yes, we have the classical systematics of following below, where we put the compounds based on chromium oxygen tetraders. It's not comprehensive. It is common and well studied. But the distribution based on layer complexes and so on and so forth can extend further and be estimated according to several polyhedra. And these uranil compounds might serve as a good example, because layer complexes and chain complexes that we identify when given the crystal description, they can be seen in the chemical and physical features and characteristics. Some crystals are based on crystal complexes, and the layer consists of different polyhedra. So I believe it's possible to put into it all together. And why oxides? Why all sulfites? Water molecules just make the contour of these chain complexes in the structure of uranopellet. These atoms of oxygen, or this three-dimensional atom, or OH group, which can be found on the atom at 2 polyhedra. They are kind of decorative elements. They are important if we talk about hydrogenic links. But I'm looking at uranopellet, and I can't say to which class of minerals it belongs. Maybe within the context of your research, can we identify a separate class of minerals based on the type of uranil? But I look at uranopellet. It creates different complexes, different polyhedra, Maybe you can say that this is a new class of minerals or type of minerals, and within its framework we can see such structural modification. Well, there is some room for contemplation, but we know that there are sulfate complexes and carbonate complexes. And I have a final remark, since it is a doctorate thesis. Is that a crazy idea that doesn't leave you something that might serve as an impetus for the future? What crazy idea have you got? I wouldn't say that it is a crazy idea, but it's interesting to synthesize all the minerals in laboratories. Not only to synthesize them, but to have a look at the thermodynamic interval of sustainability, so it's to be absolutely clear. And yes, that's a marvelous crazy idea. Thank you. Елена Владимировна. Do I get it right that I have about 10 minutes to ask my questions? Vladislav Vladimirovich. In your work, you talk about the influence of pH solution on uranil, and you talk about the pH growth from 0 to 1. In this respect, what is the cause for the increase of pH during the crystallization? Well, I suppose that it's linked to the phases formation. The complexes are taken out of the compound, and the crystallization of the phases takes this acidation to it and increases the pH of the remaining solution. So make it less acidic. Using these additional protons to form the crystal structure, thus we get the pH. Sometimes during the solution of the crystals, if these are metastable phases, we can identify these changes very simply with simple equipment. You talk about selective selenium sulfur substitution, depending on the coordination states of the tetrahedral oxyanion. Can you talk about the cause for this selective substitution?
Различный размер, да, собственно говоря, то есть.
The size is different. Selenite oxyanion is larger, and it's difficult for it to get into dense complexes. Thus, the speed is lower. This is not about the size, about the oxyanion, but its coordination. Well, I mean the coordination of the tetrahedral complex as such. We have this tetrahedral forms. And this dense structure within the tetrahedral structure cements this position. And since it has the stable complexes of uranil with no substitution, then this vacuum remains the same. It reacts on a larger cation, but it tends to preserve its size as long as possible. Well, I suppose that this is the way I can explain it according to the experimental data. What are the specific differences in the coordination of oxyanions which lead to the formation of solid solutions? Well, based on the Cesium system, I would say that that's inevitability, because, well, you can't go anywhere. And we can see spontaneous growth and the increase of speed, how selenium enters this falling position at the very end of the solution. There is so much of it, and the structure dynamically reacts and expands. And when there is no need, it remains stable. With Professor Burns, we synthesize naphthenol. We structurize the structure analogues with naphthenol sulfate, naphthenol selenite, and we get this speed of entering is lower because the influence of geometry of naphthenol ion is different. You also described the effect of the increase of the heat, the effect of heat of polyhedra of the crystallizing uranyl phase. Why is there the link between the increase of the temperature of crystallization and the change of the types of polyhedra in the structures? I would say that it has additional energy in the system, which can be eradicated by bonding. More energy than the polyhedra combine, and only at room temperature we have such apical bonding. Why sulfur is such a common constituent element in oxygen compounds of uranium? Because of this mineralogy of these deposits, there are many sulfates. And because of hydrothermal work, and thus uranyl selenite crystallizes. I can say that pyrite is the first one, and it was identified at all the deposits. What pH levels are common for the mines? In one of my reports, I pondered upon this idea about these processes, and it is linked to the idea what was before, the chicken or the egg, and the oxidation of these minerals leads to emergence of sulfuric acid, and the pH of 2,3 was identified in deposits. And I suppose that it might locally decrease in a more dense, acidic environment. Thank you very much. I have no more questions. Alexander Grigorievich? Yes, I have a couple of questions. Have you tried to crystallize any non-acidic solutions? Yes, we tried to, but it is not applicable for our selenites and sulfur. And if we talk about alkalinous systems, phosphates may grow in such alkalinous systems. There was a paper on mineralogy on uranium deposits in based on the chemistry. And there was a diagram proposed how the shift of mineralization takes place depending on the pH in the deposits. And our selenite compounds crystallize very well. If you have a clear system, subsequently something has to crystallize if you have uranyl sulfate. Well, I would like to say that it's very rare that we can crystallize anything. It might stay there for months and then it becomes a kind of a glass mass which can be just thrown away. It's not a question, but this is polymerization as well. So if the temperature is high, why do you have edge joining? And with lower temperature you have apical joining. I suppose that this is the same question, basically. Well, I can say that it is linked to the energy of the system, so additional energy is compensated by such energy demanding joining, edge joining. Are there any works on the study of solubility? Which complexes can be found in the solutions at higher temperatures and low temperatures? Of course, there are works on the study of solubility, which was done. We didn't evaluate it on our systems, we wanted to, but we never did it finally. It would be very interesting to check it on mixed systems as well. We have a number of joint works with the Professor Burns group, and we conducted thermodynamic studies for them using colorimetrics. But this was all that we got to. Probably we should focus on this as well. It would have been a very good asset to our research. Are there any more questions, Alexander Gurzhiy? But I have a question. But I may ask this question a little bit later. Dear colleagues, I'm addressing my colleagues in the hall. If you have any questions, you may ask them. Do we have any external reviews? No, we didn't get any. If none, then we move to the second stage. That's voicing the reviews by the members of the Decision Council. I would like to point to the fact that all the reviews were published on the website, and the applicant is now well aware with the reviews. You don't have to read everything in details, but pay attention to the parts which you find most important. And I suppose that Vladislav Vladimirovich provides responses to all the reviews once all of them are voiced. So I'd like to give the floor to Stanislav Konstantinovich Filatov first.
Еще раз внимание на ту ситуацию, которая сложилась в некоторых заведениях.
I would like to pay attention to the situation with some of the compounds where the apical joining is substituted by edge joining. And I hope that you'll be able to expand on it after the defense and pay more attention to the pressure, because the increase of edge joining is common. According to the recent data, maybe not so recent, Professor Hoopers identified edge bonding of tetrahedra, but not of silicates, which cannot be explained by the influence of temperature only. Temperature is not the only driving force, the pressure as well. Secondly, I would like to wish you to continue such prolific and extensive work, and in time we could be able to compare the natural and synthetic compounds. As you made for a number of classes, maybe you can focus on that in future as well. What doctorate degree is a fine art work, but as many say, that there is nothing fine art in this work, in this world, and I hope that you will continue research in this field, in this area. It's very pleasant to see when a pupil continues the work of his teacher, mentor. Sergei Vladimirovich created this study on the complexity of chemical compounds, the complexity of minerals. And you build upon this analysis, and I want to believe that you will continue this work in the future. What your mentor started will be continued by you. Much good can be voiced about your work, but I can say that I'd like to start with a quotation by Zvergin, who once said to one of the doctorate candidates, "Look, he has 10 structures. He decoded them. This is a gift to the humankind. Give him a doctorate." Vladislav Vladimirovich has not 10, not even 100, more than 100 of crystal structures. Not only computerization, not only automatization drives the progress, but such scientists drive the progress. Such enthusiasts as our applicant is. It's not just a large number of a crystal structure. It is an insane number of crystal structures. Each structure required a part of the life of the applicant. And I would like to quote a song. We sing a hymn of praise to all those crazy creators. Thank you for your marvelous, extensive work. Thank you, since I've considered. Please, Vladimirovich, the floor is yours. Since the review is published, I'll try to be very, very brief. Well, the work is highly interesting, and it follows the school by Krivovichev, uranium is the thing that binds us all together. And there are still some difficulties about the crystal chemistry. And the research paper put an order in the whole class of compounds, and its influences the structural mineralogy. We declare the first technical break. Time is of
Александр Григорьевич, вы нас слышите, видите?
Да.
Alexander Grigorich, can you see and hear us? We can see and hear you. Everything is fine. I'm sorry. Now I'm accessing through my telephone. I'm very sorry. We declare the end of the technical break. The time is 17:29 Moscow time. Denis Valerovich, you may proceed. Well, I talked about this paper as a very important paper for mineralogy as such. But I'd like to voice some of the questions and remarks. In order to systematize the structures, the mechanism of anion topology and the theory of graphs were used. And I would like to have a more generic results based on this analysis. Probably it would have been better to use the instrument of coordination sequences so as to make this aspect more logical. The second idea is linked with the first provision for defense. We believe that it would be better to use additional arguments. And another option, selenium-4, was present in some cases. The orientation of non-shared pairs was also described. Maybe the stereochemic activity could have been characterized in the terms of their quantity. But nevertheless, I'm absolutely sure that Vladislav Vladimirovich do have to read this statement. Then the thesis by Gurzhiy Vladislav Vladimirovich on the topic, the crystal chemistry of natural and synthetic uranyl, sulfates, selenates, and selenates meets the basic requirements. It's published by order number 11181/1 on the procedure for awarding economic degrees in Previous State University. The applicant for the Gurzhiy deserves to be awarded the economic degree of Doctor of Geological and Mineralogical Sciences and Scientific Major Mineralogy, Crystallography 164. Geochemistry, geochemical methods of mineral exploration. And clauses 9 and 11 were not violated.
Борис Евгеньевич, пожалуйста.
James Valerius, thank you very much. Boris Vladimirovich, the floor is yours. Dear colleagues, I'll be very precise. All the details will be very brief. And I've known the applicant for a long time. And the quality of the work is really high. I would like to focus on one aspect, I suppose, that without the studies of uranium compounds, it's impossible to solve the problem of successful development of atomic energy. And despite its development around the world, the number of academic studies on this issue is decreasing. In this respect, this work of Vladislav Vladimirovich is a very favorable exception, and these ideas can be found in the research papers of students, and the results obtained play a very important role in the development of mineralogy, geochemistry, and crystallography. I would like to say that after the pre-defense, Vladislav Vladimirovich made a lot of improvements, and it's very difficult to find ground for further remarks. What I want to say that probably it's not necessary to focus only on the nuclear fusel cycle. Uranium is a unique material that can be used in different spheres. For example, paints for porcelain or uranium glass, which were used in the 18th, 19th century. What is more, in 1999, during the war in Yugoslavia, large territories of this country were contaminated by depleted uranium because piercing shell core contain metallic uranium, and now we can see the secondary mineral formation on these territories. So thus this is much broader topic. But I'd like to say that the work is of high quality, and I will voice the necessary phrase. Thesis by Vladislav Vladimirovich Gurzhiy, the topic crystal chemistry of natural synthetic uranyl sulfates, selenites and selenates, meets the basic requirements established by the order number 11181/1 on the 19/11/2021. The procedure for awarding academic degrees submitted to the State University. The applicant, Vladislav Vladimirovich Gurzhiy, deserves to be awarded the academic degree of Doctor of Geological Mineralogical Sciences and started as Major 1.6.4. Mineralogy, Crystallography, Geochemistry, Geochemical Methods of Mineral Exploration. Clause 9 and 11 of the above-mentioned procedure were not violated. I'd like to give the floor to the members of the Decision Council in the remote access mode. Helena Vladimirovna Sokolova, the floor is yours. I'd like to voice some information from my review, since my review was published in English, and I'd like to voice it in Russian. The behavior of uranium in the surface environment is of particular importance in the health of the society, and the work done by Gurzhiy, presented here, directly addresses this critically important issue. The fact that uranil can easily be found in water solutions, and in case of a fracture, any waste containment vessels, it can lead to the formation of extremely reductive and toxic compounds outside the breach containment vessels, and their subsequent dissolution and dispersal via superficial waters and groundwater and via wind in arid environments. Mining of uranium might cause similar problems. Mine waste contains small amounts of uranium, and this will oxidize in contact with water and air, giving rise to soluble uranyl compounds that will disperse via water and wind. Different types of repositories for radiogenic waste have been proposed in different countries. Because of the long half-life of radioactive uranium, such repositories may safely contain radiogenic waste for many thousands of years. And any leaks from such repositories must be contained as quickly as possible. And transport of leaked uranyl compounds must be stopped by chemically reacting these contaminants to form more insoluble compounds, which will not be transported further. Many different geological repositories have been proposed with different mineralogical and geochemical characteristics of the host environments in which they occur. The estimate of the rating and the leakage of uranium will depend not only on uranium itself, but also on mineralogy, geochemistry, and superficial drainage of the surrounding rocks. As a consequence, a detailed understanding of the compounds that may form from uranil in a wide variety of geological environments is crucial to safely containing early leakage of uranium from such repositories. The same argument can be applied to the prevention of migration of uranyl compounds from mine waste. The work by Vladislav Gurzhiy indicates the type of work that will be needed in the future to address this crucial issue around all nuclear waste repositories and white waste sites. The applicant synthesized 107 uranyl compounds in conditions, particular temperatures, that are directly relevant to their crystallization and behavior environment typical of a breached repository. The applicant has greatly enlarged our knowledge of the types of compounds that are likely to form if uranil is released to an environment containing sulfur and selenium, and this in turn will allow to design a strategy for the effective fixation of uranium in such an environment. The thesis by Vladislav Gurzhiy on the topic, the crystal chemistry of natural synthetic uranyl sulfates, selenites, and selenates, meets the basic requirements established by the order on the procedure for awarding academic degrees at Universitetskaya University, and the applicant, Vladislav Vladimirovich Gurzhiy, deserves to be awarded the academic degree of Doctor of Geological and Mineralogical Sciences in scientific major Mineralogy, Crystallography, Geochemistry, Geochemical Methods of Mineral Exploration. Clauses 9 and 11 were not violated. I have no additional remarks or questions. Thank you. Thank you very much, Helena Vazina. Alexander Stickenberg, the floor is yours. Well, first of all, I would like to say that the paper is very comprehensive. Many structures, many compounds were obtained of a similar chemical structure, and the crystal structures were analyzed, and this is a great thing, because only in such a situation it is possible to analyze anything. If the structures are different, then it's difficult to find the ground for conclusions. So the approach is well-grounded. The second positive trait of this research paper is that the author tries to link the structures with the environment of formation. Although it's not the topic of crystallochemistry thesis, but the fact that there is such an approach is positive side. And the link between temperature and type of joining is a very interesting idea in terms of identifying the link between the structure and the formation. Of course, I would prefer the paper to contain more chemistry, the information about the solubility of these complexes, and the global idea that what is found in the solution is crystallized. As for remarks, I have doubts or misunderstanding about the complexity and how it is used. But complexity is the thing which can be intuitively used when we describe the structures. But why do we use the information entropy by Shannon? How can we compare the complexity of the structures of different different composition? So what is the complexity? How are we to compare the figures that we get? And what conclusions can we draw upon those? We can make quantitative conclusions, but then we don't need parameters. And if we talk about qualitative conclusions, then the parameters are of no such importance. The concept that the author offers is not quite clear to me in respect of complexity. That's the largest, I suppose, question or remark to the paper. But on the whole, I agree that the thesis corresponds to all the requirements. Do I have to read this paragraph aloud, or I can just say that I agree that the applicant can be awarded the scientific degree of the Doctor of Science. Well, the members of the Decision Council have voiced their opinions, and I would like, as the head of the chairperson of the Decision Council, have to voice my opinion. I would like to voice some of the ideas that I mentioned in my review, although some of them are very similar to the ones previously voiced by my colleagues. Well, I'm absolutely sure that the applicant deserves being awarded the degree of the Doctor of Sciences. But I have two remarks that I find very important. The first one is of crystallochemical analysis. In his work, the applicant divides sulfates compounds into chain compounds, isolated clusters, and sheet compounds. And the examples can be found on illustration 2.1, and they depend on they are formed with two types of compounds. These are uranyl and compounds of sulfur. These are kind of two building blocks. With such an approach, when we identify these clusters, it becomes a little bit more subjective, and it describes specific crystal structures. And very often it is the case that it's possible to disregard some general features, since this approach is not very strict. But I would like to see the general traits in this doctorate thesis. And the second idea is mostly linked to genetics. Well, I'm in favor of using crystal chemistry, which was done in the first provision for defense. And I think that this idea is very attractive. But the thing is that it is poorly grounded in the text of the thesis. And the chapter crystallographic approach to the formation of minerals of Uranil, and in the conclusion to the thesis, the applicant uses such structure as we can suppose should take place, most likely, and so on and so forth. So the applicant uses a lot of modality, talking about these ideas as of a working hypothesis. So the applicant himself understands how feeble this provision is, because the formation of new formations of uranium depends only on temperature, and in my opinion this is not enough, and pressure is important, and whether the environment is alkalite and other factors influencing it. So this one-sided approach is a very weak point of this provision. And the main argument for this provision is based on the results of the experiments. And as a great researcher, he understands that these experiments might not have equilibrium, that they might not recreate the conditions. And if a mineral was identified only once, then we can't talk about consistent pattern. We need statistics on different deposits, different associations, and thus we can form some kind of pattern. So in my idea, this provision for defense was not fully argumented. And my strategic question is, was it necessary to include this provision for defense in the work? Well, I like this idea. Probably this idea is a little bit of a crazy idea, which I asked you about. And my final statement as the chairperson of the Dissertation Council, I have to voice it. The thesis by Vladislav Vladimirovich Gurzhiy on the topic, the crystal chemistry of natural and synthetic uranyl sulfates, selenites and selenates meets the basic requirements established by Order number 11181/1 on the 19th of November 2021. The procedure for awarding going to the State University. The applicant Vladislav Gurzhiy desired to be awarded the academic degree of Doctor of Geological Mineralogical Sciences, Center of Specialty 164, Mineralogy, Crystallography, Geochemistry, Geochemical Methods of Mineral Exploration. The clauses 9 and 11 of the specified orders were not violated.
Мой отзыв, и теперь настало время.
That's my review, and now we give the floor to Vladislav Vladimirovich. You have to respond to the key remarks, maybe not all of the remarks, but the key ones. Dear colleagues, first of all, I'd like to thank you for the critical approach, positively critical approach to my work and to my thesis. As for the responses, probably I'll start with your question. Of course, probably there is the absence of fundamental boundaries, and probably the lack of basis depends on the experimental characteristics of my work. Much was done in laboratories and much was taken from the experiments taken by my colleagues. The question is, should we rely on the work of our colleagues? And if we are to rely on their work, then that's it. But as an scientist who works on practical aspects, I do understand that much might change, even with the slightest differences in the conditions of experiments. This is why I used modality when forming my provision. So we tried to rely on the work of our predecessors, of our colleagues. And if future colleagues find some discrepancies, and we'll be just happy to improve on the results of our experiments. Last year, we started working on uniting our scientific groups, and our students went to Samara to work on joining our two fundamental crystallographic schools to use different approaches to for our future work, and I hope this will only enhance our future works. As for the complexity of structures, I believe that this is the approach which is most closely to our crystal chemistry. And we talk about the ratio of the position, what we use in any structure review. So this is a very obvious aspect. And the approach based on the structure of the element only is the basis. And maybe later on, with the help of our colleagues, with Sergei Vladimirovich, we might develop this theory and look at other nuances. If we take into consideration isomorphic substitutions, for example, so we might expand on this issue. And if we look at it in a fundamental way, I suppose it should not contrast with crystal chemistry description of structures. And as for Boris Evgenyevich's comment, when we were once going around the Czech Republic, we could see a lot of art objects there, beautiful glasses and porcelain plates from uranium-containing glass and porcelain. I wanted to buy a couple, but other family members disagreed. That it's a beautiful work of art, and I hope that we'll be able to focus on these aspects of uranium as well. Thank you very much for your warm, kind words and your characteristics of my work. I'm addressing the members of the Decision Council. Is everyone satisfied with the answers of the applicant? Colleagues in the remote access mode, yes. Then we can move to the next stage of the procedure. Is there anyone willing in the hall to say a few words? Igor Viktorovich, the floor is yours. Please introduce yourself. There's no need for me to introduce myself. Igor Viktorovich Pyakov, the Chief Scientific Officer of Geological Faculty of Moscow State University. Corresponding member of the Russian Academy of Sciences. Mineralogical scientist. Geochemistry scientist. Consumer of crystallochemistry information that colleagues provide us with, in particular Vladislav Vladimirovich. Modern mineralogy without crystallochemistry cannot exist without each other. And each crystallochemistry research of natural and synthetic compounds. I'd like to stress two ideas. Firstly, geochemistry focuses on the link of topology and solubility. The information on topology, on the type of joining, polyhedra, be it apical or edge, this is about the density and solidity of bonds, which results in solubility. By analyzing that, we understand how particular solid phases behave. If we talk about hyperkinesis, the issue is about the pressure are not important. These are isobaric systems, and there is no pressure apart from capillary pressure. If we talk about synthesis, then the situation is different. And you could have used such simple things as the temperature of the system where the synthesis is being taken and how dense is the system, since graphs are present for both. Then about selenium. Why is it important for those who study mineralogy? Sulfur and selenium befriend, starting from endogenic processes, and they interact in hydrothermal decarbonate objects. Zhilin, Demkov and Rizhov wrote about this, and hypergenic formations hypergenic ores, not only Utah, not only Katanga, are the places where they can be found. There are some geographical places in our country where we can find such elements. And I would like you to focus on selenite and selenate work, and selenium and sulfur are different. The rule of Vegard is constantly violated and the cause is clear. And this a very beautiful part of your work, of your research paper. I don't want to take much of your time. I would like to congratulate your department, to congratulate the Institute of the Earth Sciences and the State University with the a new doctorate degree. I'm absolutely sure that the members of the Council will support your claim. It's highly pleasant that such specialists of high qualification exist. And genetic part is also present in crystallochemistry work. Not everything is explained, but nevertheless.
But
you talk about the temperature correlation, and you have the right for it. It might be explained further on, or might not be explained. Thank you, Igor Viktorovich. Thank you very much. Dear colleagues, is there anybody else who's willing to express their attitude towards the research paper? I would like to give a further remark, not as a member of the Decision Council. Our department of the Department of Inorganic Chemistry of Samarski University, is working on crystallochemistry. And I would like to say that this high appraisal is not my own opinion, because this is the opinion of our entire department, and we support this positive review of the work. As the chairperson of the Decision Council on Chemistry Studies, I suppose that this work might be used for major 144 in organic chemistry as well.
Владислав Владимирович, по протоколу я должен дать вам слово, чтобы вы ответили, но мне кажется, тут...
Vladislav Vladimirovich, you might have the floor if you want to respond. Thank you very much. Thank you very, very much for such kind words and for such a high esteem of my work. Did we receive any questions via email? No. Then I'd like to give the floor to the scientific advisor, Sergei Vladimirovich Krivovichev, Professor, the Doctor of Mineralogical Sciences, the corresponding member of the Russian Academy of Science. Dear members of the Decision Council, dear colleagues, first of all, I'd like to thank the members of the Decision Council for your agreement to work in this council. And I suppose this is the best council for this type of research paper. The panel consists of the representatives of the great Samarskaya school, Samara school of study of uranium compounds, our great structural scientists and the specialists in growth of international level. I suppose that the members of the council are all magnificent scientists. I'd like to say a few words about the work itself. The material, the crystallochemistry material, is profound. We could have put all the provisions for defense in this crystallochemistry idea, and the discussion could be based on the structures. And the majority of the remarks was linked to the first provision for the defense, where Vladislav Vladimirovich started focusing on the growth, kinetics, thermodynamics, which was a little bit dangerous in a way. It was outside crystal chemistry as such. The first version of the provision was even more radical. But it was Vladislav Vladimirovich's idea to talk about the temperature, and this is what Vladislav Vladimirovich claimed that has to stay in the thesis, the idea of the temperature. So this idea is very interesting, and the applicant, as a participant of the experiments, wanted to talk about the results of the experiments. But what is the ground for this mechanism is a different issue. Why we wanted to go beyond the boundaries of crystal chemistries? These are soluble systems, and they evolve in the course of time. If we talk about crystallization of solutions, they evolve in terms of phase. So first, some crystals are formed, then the others, some become soluble. It's very interesting to understand what forms the process is. Maybe it's linked to the structure, to the complexity. We can talk about quantitative description of this complexity. Previously, there were no quantitative calculation of this complexity. And this is a crazy idea, and the important problem, the link between the structure, not of the morphology of the crystals, not of the forms of mineral aggregates, but the structure and the peculiarities of growth, thermodynamics and kinetics. There are many factors which are important in here. pH is of importance, for example, as well. A lot of empirical observations were carried out. Oswald introduced the rule of the stages of Oswald, and he was laughed at the time. But currently, this is very important empirical observation that he conducted, the rule of the stages by Oswald. Maybe the phases that Vyacheslav Vladimirovich are metastable. It has a lot of ground for further research, but the work is very important. And one of the special traits of this work is that the change of topology of structures the sulfur selenium variability. Well, I've never seen the analogues of this finding. It's a very difficult system, I'd have to say. Of course, I'd like to say a few words about Vladislav Vladimirovich himself. He is a very ambitious person, full of energy, open for cooperation. He actively cooperates with many Russian and foreign mineralogy scientists. And the timing of his research paper coincided with the findings of uranyl phases in rarefied structures. That was a great stroke of luck. Our mineralogical scientists, Anatoly Kasatkin, for example, Igor Viktorovich described some of the phases. American scientists and the scientists from the Czech Republic also work on these phases. And I suppose that it will be interesting for mineralogy, since it's interesting to identify the processes which occur in the secondary oxidation stages. Finally, I'd like to say that the specialists of different religious groups dispute when the life starts. Some say when the person is born, others say when the second one when the life germinates, and the third says no, the life starts when the wife takes the children away to the country house. And I'd like to say that life of a scientist starts after the doctoral defense. Well, I didn't want to say anything about the family of the applicant, but it's very good tradition of our department that when scientists defend doctorate thesis at a relatively young age, they have all their remaining life to focus on the science and research. And I truly hope that the applicant will pursue this career. Dear colleagues, I'd like to address all those present in the hall. Who would like to take the floor? There are none. Then we put an end to the discussion, and we don't receive any more questions via email. We proceed with the next stage of the procedure. Prior to the final roll call, I'd like to ask the members of the Dissertation Council and the applicant. Do the members of the Dissertation Council have any objections or questions to the procedure of today's meeting of the Dissertation Council? According to the procedure, I need to receive the answers from all the members of the Dissertation Council. No objections, no questions. No objections. No objections. Irina Vadimovna? No objections, no questions. Alexander Grigorievich? No objections. Thank you. Then, dear colleagues, members of the Dissertation Council, before we start the voting, I want to ask you, do we need to make a break to discuss the results of the defense, or we can directly proceed into the voting procedure? Voting. Directly voting. Thank you. Thus, I raise the question of the time is 6 o'clock, 12 minutes Moscow time. I raise the question of awarding Gurzhiy Vladislav Vladimirovich certificate degree of Doctor of Geological and Mineralogical Sciences, Scientific Major 164, Mineralogy, Crystallography, Geochemistry, Geochemical Methods. Of mineral exploration. When you vote for, all the members of the Dissertation Council agree that the clauses 9 and 11 of the above-mentioned order were not violated by the applicant. And I'd like to quote the clause 11. In the thesis, the applicant's scientific degree is obliged to refer to the author or the source of varying materials or individual results. When using the results of scientific works performed by the applicant's scientific degree personally or as a co-author, the applicant is obliged to note the circumstance in the thesis. I'd like to remind you that the decision of the Dissertation Council on the issue of awarding scientific degree is considered positive if more than half, but no fewer than 3 members of the Dissertation Council, voted for it, in accordance with clause 23 of the procedure. So we proceed with the voting. Filatov Stanislav Konstantinovich, your opinion? I vote for. Denis Valerievich, I vote for. Boris Yevgenyevich, I vote for. Yelena Vadimovna, I vote for. Alexander Grigorievich, I vote for. And I, Brusnitsin, the chairperson, Brusnitsin Alexei Ilyich, vote for. Thus, dear colleagues and guests, out of 6 No, let me count it once again, I'm sorry. Yes. Out of 6 members of the Decision Council, voted for, 6 people. Voted against, none. Abstained, none. Decision in awarding Gurzhiy Vladislav Vladimirovich the degree of Doctor of Geological and Mineralogical Sciences in scientific major. 164, Mineralogical, Crystallography, Geochemistry, Chemical Methods of Mineral Exploration. Taken. Let's congratulate the colleague, please. And we give the floor to the applicant for the final remarks. Dear colleagues, first of all, I'd like to thank the chairperson of the Decision Council and for all the members of Decision Council, and especially to the colleagues in the remote access mode. I know it's morning for you, and thank you very much for such kind words about my work. Thank you so much. I've been thinking for a long time how to present my thanks, but my thanks can be seen in the form of such a slide. This is my department, the resource centers, colleagues, friends, acquaintances who have been of help for me throughout all these years. Of course, I wouldn't have succeeded without my scientific advisor, and I'd like to thank my family as well. While I would have never had anything, wouldn't have had any success without the support of my family. I will pursue this route. As the chairperson of Decision Council, I'd like to thank all the members of Decision Council. My special thanks to the colleagues from the US and Canada. Thank you for finding the opportunity to participate in the work of our Decision Council. I declare the meeting closed. Thank you.